Okay, so I'm going to go over here quickly how, or not so quickly, and try to um, go over how we have able to solve currents in a multi-loop situation. Okay, and so we've got a circuit here, and I've already done all the labels just to save time. Um, um, Essentially, we have a circuit, okay, and there is 1, 2, 3, 4, 5 resistors, and 1, 2 EMFs, okay, and those values are over here, okay. And so what I have done is started by labeling my resistors R1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 4, 5, and labeling my corners or in my junction points, right? So A, B, C, D, E, F, just around, okay, and that's what I'm going to be able to use to describe the loops in the in the circuit. Um, and I've labeled the currents that will flow. So to label the currents, I started over here just at point A with one of the EMFs, and current, I'm just going to use the um, standard that current flows away from the positive, so and to the negative. So up we have I1 coming out over here because it's the first current I talk about, and it moves over here. And I notice that I'm going to have a junction point, so I'm going to stop for a second. And then I move over here to the other E, MF, and I'm going to call this current I2, and it's going to move out and down and over, and it's going to hit a junction point. Okay, so then I'm going to stop for a second. And if I go back over to IE, I realize that I can go in the opposite direction, okay, so backwards to this junction point down here of E, and the I is going to flow into it. So this is still going to be current I1. So this half of the loop on this side has current I1 running through it, and this side here has current I2 going through it, okay? And then they go, I1 and I2 meet, and they're sort of, it has an additive property, a conservation of energies, as they move between point B and point E, okay? And so the first thing, and then that is what I'm going to call current I3, and it's moving in this direction based on the what I've drawn here, okay? So I've got I2 going in, and I3 and I1 coming out, and I1 coming in, and I3 coming in, and I2 coming out, okay? And so the first thing to do is we're going to check to verify Kirchhoff's first law, which is conservation of currents at branch points. So I've done that down here, where I have taken branch point B and redrawn it, and branch, which is this point, and branch point E, and redrawn it. So I'm going to look here. So I have I2, which is coming out. So I2 is going to be equal to I1 plus I3. Okay, so that's what we've got over here. And then if I look at point E, I have I3 coming out and I1 coming out. So that means 1 plus 3, because they're leaving, must be equal to I2 coming in. So in both cases, I have I2 equal to I1 plus I3. Okay, so I1 is in red, I2 is in teal, and I3 is in blue, and I'm going to use those colors every time we mention those currents for the rest of the demonstration, so that maybe it'll to help those that are sort of visually see what is going on, and it's kind of hard to distinguish all of these eyes as we move around. Okay, so the first, after we've verified our conservation at branch points, the next step is to identify the loops and use the loop rule. Okay, and so what the loop rule is it's a conservation of energies. So that we're going to calculate the total potential for each resistor and the potential in the loop. So it must be equal to 0, right? So our potential in and our change in potentials must be equal to 0, and that's just essentially summing the VIRs all around. Okay, and so there are two loops here to consider. Okay, and the first one is ABEF, and that's ABEF, that is loop 1, and BCDE, BCDE, and that's what I've defined as loop 2. Okay, and so now I'm going to traverse these loops. Loop 1, I'm going to traverse A to F, and I'm going to do it clockwise. And then I'm going to traverse B, C, D, E, and I'm going to move B to E clockwise. So I'm going to go from A to B to E to F, We're going to go to B to C to D to E, and then, of course, back to the starting point to finish the circle. So I'm just going to go. I've already done those loop rules. Okay, so I'm just going to quickly sort of show, we're going to go branch by branch and where each one of these pieces come from. So I start at point A, okay, and I move from A to B, and as I move from A to B, I encounter resistor number 1, and I'm going clockwise, and I'm looking at current I1 moving in the same direction as my clockwise movement, okay? And so that means I am going to subtract IR, okay? So if we look at those traverse rules, when we cross a resistor in the same direction as current, we're going to use the opposite of the voltage, okay? So that's minus, in this case, I1 R1, so I1 R1. Continue going, we get to point B, and then we come down to traverse from B to E, and we come across I2. We come across I2, we've now got current I3, and it's coming against us, okay? So you see we're still going clockwise. I3 is pointing in the opposite direction of our clockwise statement, so when we do I3 R2, we're going to add it. So down here we have plus I3 R2. All right, and then we keep going down to E, and then we go from E to F, and we encounter another resistor. This time the resistor is back to I1, and I1 we're moving again in the same direction as that current as we go over I3. So we're going to subtract I1 I times R3 over here, and then we're moving up to F and going from F to A, and we're still at current I1, and it's still moving in our direction, and the first thing we hit is resistor R2, so we're going to subtract I1 times R2, and then we're going to go across our EMF potential. And if we look at our loop rule traverse laws, if we cross from a minus to a positive as we go doing our traverse, we add the E to the EMF here. And that all gets set equal to 0 to conserve the energy. Okay, so all of those changes must be equal to 0. All right, so that's loop 1. Gives me this long equation. Loop 2, we're going to do the same thing. I'm going to start at B, and I'm going to move over. Okay, so as I start with B and go clockwise, the first thing I encounter is R1, and this is with R2, and it's in the same direction. So I2 is moving to the right, counterclockwise is moving to the, or clockwise is moving to the right. So R1. So I have I2 times R1 minus. That's what I have here. And then I cross my EMF from negative to positive. And if I look at my traverse rule, when I cross the EMF from negative to positive, I add E1. So it's just E1 plus. And then I move to C, and there's no more. As I move from C to D, we encounter one resistor under the current of I2. So it's I2 times R4. And again, we're moving down from C to D, and we're moving, the current is moving in the same direction, so we're going to subtract I2 times R4. So subtraction of I2 times R4. Then as we move from D to E, we encounter another resistor, R5, and so and I2 is again moving in the same direction. So we subtract minus I2 times R5, so it gives us R2 minus R5. And then we go from E to B to move back to the beginning, and as we go clockwise up, we see we're moving in the same direction as I3, and we encounter R2, so we're going to do R3, R2 minus, because we're moving in the same direction as our current is moving here, or our anticipated current, and again, we're setting that equal to 0. So essentially, remember, this loop rule, right? We have a voltage input, and we have all of these voltage drops, okay? So we have a V equals IR over all of these voltage drops, and our conservation says that the drop in all of these voltage has to be equal to the input in the voltage, right? So essentially, setting this whole equation equal to 0 incorporates that, right? It's a conservation of potential energies in our system. I can't have voltage potential left over after I've gone around the circuit. It has to all be lost. Okay. So here, now, what I'm trying to do is find out the value of current I1, I2, and I3, and now I've got these long equations. Okay, so what I'm going to do is I'm going to try to look at each equation, all right, and see which loops contain which values. So I can see that I1, or that loop 1, has I1 and I3, but it does not have I2, And loop 2 has I2 and I3, but does not have I1. So that means I can rearrange these equations in terms of I3. So I can set I1 equal to I3 and I2 equal to I3, and then I'm able to use our original equation to plug I2 equal to I3 and I1 equal to I3 in up here and solve this to get our actual current for I3. Okay, so again, we have 3 variables, 2 equations, and algebraically we can solve for I3. Okay, and then after we solve for I3, we can take that value and plug it back into these equations to solve I1 and I2. Okay, so we're going to go through how we do that step by step. All right. So all of this is going to be scanned in and available so you can print it out or look it out, and so you can have it more directly as I talk about this. All right. So this is what I just told you what we're going to do. We're going to look for we look and realize that we say I3 is in both and I1 and I2 are indifferent, so we're going to solve loop 1 for I1 and loop 2 for I2 and put them in terms of I3. Okay. So loop 1 was this here. Okay, this is just rewriting what we had on the previous page, and I'm going to rearrange to get I1 alone. Okay, so I1, okay, just pulling out minus I1 here is minus I1 R1, R1 R3, R2 R2, and then again plus I3 R2 plus E2. So this is again just algebraic, and then I'm going to at this point input all the values that we know, right? So we have all of the R values and we have the E value, and then from there I simplify down, right? So I combine and then I subtract I3 and I subtract 120 to move them to the right side of the equation. Then I divide both sides by negative 30.2, so the negative is lost on this side, and so is 30.2, and then minus 30.2 over minus I, 30.2, and then I'm just going to simplify things, add minus 120, okay, because that's just algebraically rearranging. It makes the division a little more straightforward that we're losing we have a change of sign. So a minus 120 over minus 30, and that simplifies to I1 equals 0.06 I3 plus 3.97. Okay, so that's the value of I1. And this is the value that I'm going to plug back into the I2 equals I1 plus I3 equation. Okay. And now we do the same thing for loop 2, where I have I2 R1, E1 I minus, okay, so this is the same equation that we wrote, and again, rearrange to put I2 alone in terms of I3. So I just start here and pull out minus I2, and then I pull out R1, R4, R5, and I'm left with E1 minus I3. This plug in all the values that I know, okay, and then do the condensing. All right, so here I'm going to move I3 and 120 to the right side of the equation, and I'm going to divide both sides by minus 40. And when I do that, okay, I get I3 over 2 minus 40 plus minus 120 over minus 40. And again, this is just rearranging minus 120 to plus a minus 120 so that it's clear that we have a change of sign when we divide by minus 40. Okay, and so we have I2 equals minus 0.05 I3 plus 3. Okay, so then we can take the value that we just solved for I1, the equation that we just solved for I1 and the equation that we just solved for I2, and we can put them into this equation, I2 equals I1 plus I3. Okay. So I've done that here in we solved loop 1, okay, and we said I1 was equal to 0.06 I3 plus 3.97. So for I1 here, I've put in 0.06 I3 plus 97, and that's this value here. Okay, that's I1. And then I2, we've just said is minus 0.05 I3 plus 3. That's alone on this side, so I just substituted this value here. So I have minus 0.05 I3 plus 3 equals 0.06 I3, 3.97, and I3 is there on its own as I3. And then we just do the simplification, right? So it's just algebraically manipulating, adding and subtracting the 3 and the I over things to simplify it, and we get I is minus 0.87. Okay, so what here, this minus 0.87, it's important that we keep the sign here because it's going to be important for the conservations of energies. But what it's telling us is that there's a 0.87 magnitude current flow, but it's in the opposite direction that we have written in our circuit. Okay, so if we go back and look at our circuit, I know our arrow is going this way, but our current is actually moving back, is actually moving in this direction down here. Okay, so there's 0.87 amps of current moving down here in this direction. And so again, the minus sign doesn't, we can't have a negative current, but it just means that the sign is opposite of what it is written on our circuit. Okay. All right, so we solve for I3. Now we can take that value, is minus 0.87, and solve I1 and I2 directly. So again, we have the equation for I1 that we used, which was 0.06 I3 plus 397, and that was just when we simplified the loop rule for loop 1, and we just plug in 0.087 for I3, it gives us this value of 3.91 amps. And we do the same thing for I2. So again, this is just the equation that we solved on the previous page, and it's minus 0.05 I3 plus 3, putting in minus 0.07 over here, we get I2 equals 3.04 amps. Then we have to verify that we've actually done everything correctly, okay? And so our conservation of energy says that I2 must be equal to I1 plus I3. So I2 is 3.04 amps, I1 is 3.91 amps, and I3, as we solved, was 0.087 amps. So when I put all that in, if I do 3.91 minus 0.87, it's equal to 3.04. And there we go. I've gone through, we have now solved what all three currents are in the equation. And again, right, so it's important to note that we need to maintain the negative I.87 here, right, for consistency of our conservation of energies, all right, but all that's telling us is that the direction of current that we've assigned in our circuit is in the opposite direction. Okay, it does not mean that there's a negative current flow. Okay, you assume that the current is moving in the opposite direction. All right, if you still have questions after that, please let me know and we will work it out. Have a great weekend.